Welcome back. Now we are going to start discussion on types and design of fits. We are having two systems, basic hole system and basic shaft system. A basic hole system is a system of fits in which the design size of the hole is the basic size and the allowance, if any, is applied to the shaft. So size of the hole is the basic size and we apply tolerances to this hole first and then to the shaft. Basic shaft system is a system of fits in which the design size of the shaft is the basic size and allowance, if any, is applied to the hole. So we will focus on the basic hole system in our discussion on the design of fits. So the basic hole system uses the minimum hole size as the dimension from which to calculate the allowance and to establish tolerances which will produce the desired fit. So we will be starting with the size of the hole and then we will be applying tolerances to the shaft. In the figure, the basic dimension is 2.000 inches. This dimension has been applied to the hole. So this is basically the size of the fit. So that becomes the basic size of the hole. And as I mentioned already in the previous segment that we will be using unilateral tolerances in the design of fits. So the upper limit is added to this basic size of the hole and there is zero lower limit, or there is no actually lower limit that is applied to this basic size. Now, depending upon the type of fit that we are going to design, we will determine the basic size of the shaft. Now, if we are going to design a clearance fit, then the tolerances will be applied to the shaft such that whatever combination of sizes we achieve, the shaft will always be smaller than hole. Or to be more exact, the limits are applied in such a way to design clearance fits that the largest shaft that we can make will be smaller than the smallest hole that we can make. Right? So the smallest hole that we can make in this case is having a size of 2.000 and the largest shaft can have a size of 1.997. So that is the minimum clearance, that is actually 0.003 that we can achieve in this case. So that is the case of a clearance fit. When we are going to design interference fit, then the shaft will be larger than the hole, or to be exact, even the smallest shaft will be larger than the largest. So we will see this concept in detail when we will solve examples of design of fits. There are three types of fits: clearance fit, interference fit, and transition fit. A clearance fit is one having limits of size so specified that a clearance always results when mating parts are assembled. It is used to permit relative freedom of motion between a shaft and a hole, axially, radially, or both. An interference fit is one having limits of size so specified that an interference always results when mating parts are assembled. It is used to secure a certain amount of tightness between mating parts. Either these are meant to remain permanently assembled. So that is one of the uses of interference fits, or to be taken apart from time to time. Or two parts may be required to fit together snugly without apparent tightness or looseness. So there are different classes of clearance fit and interference fits. So the degree of clearance in the case of clearance fits and degree of tightness in the case of interference fits varies from class to class. A transition fit is one having limits of size so specified that either a clearance or an interference may result when mating parts are assembled. So we will primarily focus on clearance fit and interference fit in our discussions. So we will be using the standard ANSI B4.1 in our discussions, and you can refer to a machinery's handbook for details about this standard. So I have taken tables from machinery's handbook, the tables related to standard ANSI B4.1. And once again, you can refer to machinery's handbook if you need the tables of these different types of fits. There are two things that are required to design a fit using this standard. So the first is the type of fit, and the second is size of fit. And as we are using ANSI B4.1 and this standard is basically a basic whole system, so size of fit actually will determine the basic size of the whole, and then we will apply limits to get the sizes of both hole and shaft. So we require type of fit and size of fit. There are three groups or three families of fits in this standard that we are going to discuss. So we are having running and sliding clearance fits, we are having locational fits, and we are having force and shrink fits. And there are different classes or subtypes of each of these group or family of fits. RC fits are all clearance fits. Now the amount of clearance varies from specific class of RC fits. So it is different in different classes of RC fits, but all are clearance fits. Locational fits could be clearance fits, they could be transition fits, or they could be interference fits. So LC fits under locational fits are all clearance fits. LN fits are all interference fits, and LT are all transition fits. FN or force and shrink fits are all interference fits. All classes under FN fits are actually meant to design interference fits. So we need alphanumeric designation to designate these fits. So for example, RC1 means this is RC fit, running and clearance fit, and class 1 of RC fits. Similarly, FN4 represents class 4 force and shrink fit. Similarly, LC3, for example, will mean class 3 locational clearance fit. So first we will discuss clearance fits, that is RC fits and LC fits. So C designates the type of fit, that is clearance. And T stands for transition, and N designates interference fits. So first we will discuss RC, running and sliding fits. Running and sliding fits for which limits of clearance are given in table 8A from machinery's handbook are intended to provide a similar running performance with suitable lubrication allowance throughout the range of sizes. They are further designated as RC1 to RC9, with the closest fit being RC1, progressing to the more open running fit RC9. So we have to understand the design of fit. So let's solve a simple example. A 2-inch shaft and bushing are to operate with a class 4 running fit. Make drawing of the bushing and shaft and do analysis of the allowances. So the type of fit is RC, and the size of fit is 2.00. So this is the table from machinery's handbook. So table 8A is for running and sliding fits. So first we need to know the size of the fit. So that is 2.00. So that has to be looked up in this first column, that is nominal size ranges in inches. So 2 lies here in between 1.97 and 3.15. And the second thing is to look for the tolerance under the required class of the fit. So class of the fit is RC4, and we come across these different values. So as we are using basic hole system, so first we have to determine the size of the hole. So the basic size is 2 inches. So the size of the hole that we will obtain will be 2.00. Now we need the value of limits. So you could notice here two values are given under hole as well as under shaft. So these values are in thousands of an inch. For example, 1.8 means this will be equal to 1.8 divided by 1000, so that will be 0.0018. So the limit applied to the hole will be 2.000 plus 0.0018 and minus 0, because we are having a unilateral system. Similarly, for the shaft, we have to make a couple of small calculations. Now, first we need to determine the basic size of the shaft. Now, that will be equal to the upper limit of the shaft. So, upper limit will be equal to 2.0. And you could see here minus 1.2. So, that is actually minus 0.0012. So that will turn out to be 1.9988. So that is the basic size of the shaft, 1.9988. Now, again, we are using unilateral system, so upper limit will be 0. Just remember the basic rule that we discussed, that we have to apply limits like that, we have to apply limits in the direction that is less dangerous. So we have to achieve a clearance fit. So we have to make sure that hole is larger than the shaft. So we have applied limit in the positive direction to the hole, and we will be applying limit in the minus direction to the shaft. So what will that value be? So that will be the difference of these two. So that will be equal to minus 2.4, minus 1.2. So that will become minus 1.2, or that will be equal to minus 0.0012. So the lower limit will be, the lower limit of the shaft will be minus 0.0012. So we have obtained the size of the hole as well as size of the shaft. Now we will make a small simple analysis of the tolerances that we have applied to both hole and shaft. So the smallest bushing that we can achieve, let's first draw these hole and shaft. So the size of the hole is 2.00 plus 0.0018 minus 0.0, and for shaft it is 1.9988 plus 0 minus 0.0012. So the smallest bushing, or smallest hole actually, that we can achieve will have a size of 2, that is the lower limit of this hole, so that is 2. And the largest hole that we can achieve will have a size of 2.0018, or its upper limit. Similarly, the largest shaft that we can achieve will have a size of 1.9988, and the smallest shaft that we can achieve will have a size of 1.9976, that is 1.9988 minus 0.0012. So that is 1.9976. Now the difference of the smallest hole and the largest shaft will give us the minimum clearance. So the difference of these two is 0.0012. And the difference of the size is the largest bushing or the largest hole and smallest shaft will give us the maximum clearance, and that will be equal to 0.0042, and we can verify this from the table. So you could see here under the column of clearance that the minimum clearance that we should get is 1.2, that is 1.2 divided by 1000, so that will be 0.0012, and the maximum clearance should be 4.2 or 4.2 divided by 1000, so that will be 0.0042. Or in other words, we can say that when both bushing or the hole and the shaft are made at MMC, we will get the minimum clearance. And when both are made at the LMC, we will have the maximum clearance. And of course, clearance can range from 0.0012 to 0.0042. So we can have any other value between these two values as well. But you could notice that this is the minimum clearance. So we cannot achieve smaller clearance than this. So that is the definition of a clearance fit, that the limits are applied to the size of hole and shaft in such a way that clearance always results. So we will always get a clearance, and minimum clearance is 0.0012 and maximum is 0.0042. The second group or family of fits in ANSI B4.1 is locational fits. Locational fits are fits intended to determine only the location of the mating parts. They are primarily used for stationary assemblies. They may provide rigid or accurate location as with interference fits, or provide more freedom of location as with clearance fits. Now there are three classes of fits under locational fits. So we are having locational clearance fits, we are having locational transition fits, and we are having locational interference fits. And we are focusing now on this first class, that is locational clearance fits. So they are also clearance fits just like RC fits. So locational clearance fits are those which have their tolerances applied to the hole and shaft sizes in such a way that any combination of mating sizes produces a clearance allowance, just like RC fits. They are intended for stationary assemblies, which can be freely assembled or disassembled. And you will notice in the table of this type of fits that we get as a whole small clearance in LC fits as compared to RC fits. And they are further designated from LC1 to LC11. So again, we want to design a 2-inch fit in this example. So a 2-inch bushing and locator pin are to assemble so that two parts are in alignment. The fit is class 4 locational clearance fit. Draw the bushing and pin, insert the appropriate dimensions and tolerances, and do an analysis of the allowances. So the type of fit is LC4, and the size of fit again is 2.0. So this table is similar to the table of RC fits. So the size is 2, so that lies between 1.97 and 3.15. And the class of fit is LC4. So the procedure is the same as we use for RC fits. So we are using a basic hole system. So first we will determine the size of the hole. So hole will have a basic size of 2. So that will be 2.00 and plus 4.5. So remember that this is 4.5 divided by 1000. So this will be plus 0.0045 minus a 0. So we are adding a limit to the size of the hole because we are intended to design a clearance fit. So hole should always be larger than the shaft. So that is the basic idea in the design of clearance fits in this standard. Similarly, for the size of shaft, first we need to determine the basic size of the shaft. So that will be equal to the upper limit. So you could notice that upper limit is 2 plus 0, right? So that will become a basic size of 2 plus 0. And minus, that is the difference of these two, that is 3 minus 0, so that will be minus 3, or minus 3 divided by 1000, so that will be minus 0.0033. So that will be 0.0033 divided by 1000. So we have determined the size of the hole and the shaft. So hole has a size of 2 plus 0.0045 minus 0, and shaft has a size of 2.00 plus 0 minus 0.003. Now let's first draw this hole and shaft. So the smallest hole that we can make will be equal to its lower limit. So that is 2, that is the smallest bushing or the hole that we can make. And the largest bushing that we can make will be equal to its upper limit. So that is 2.0045. Similarly, the largest shaft that we can make or the pin that we can make will have a size equal to its upper limit. So that is 2.000. And the smallest pin that we can make will be equal to its lower limit. So that will be 2 minus 0.003. So that will be equal to 1.997. So difference of these two, the smallest bushing and the largest pin will give us the minimum clearance. So that is 0. And the difference of the largest hole and the smallest pin will give us the maximum clearance. And we can verify the results from the table. So the minimum clearance that we can get in this type of fit is 0, and maximum is 7.5, or 7.5 divided by 1000. So that is 0.0075. So in this case, the minimum clearance that we will get is a clearance of 0. And the maximum clearance is a clearance of 0.0075. So you should have noticed that in LC fits as a whole, we are getting smaller clearance as a whole. So you could try other sizes of fits using these tables, and you could notice some other interesting features, some other interesting patterns in these tables as well that we didn't discuss. That is how, for example, clearance is changing as we are moving from LC1 to LC11, and how that is changing as we are moving downward. That is when the size is increasing. So you are encouraged to go through these tables if you are interested for more information. Thank you.